Very good morning, Dr. Jignesh Bhatt. Sir, am I audible?
Good morning, Ishita.
Very good morning, sir. So you can start presenting. Let's just make sure that your video is working fine. First, we'll be starting the meeting soon. Hello, good morning, sir.
Good morning. Is it
Yes,
fine?
yes, sir, it is. It is. So before starting our session, I'd like to introduce our speaker to our respected participants. Just let's wait if all the participants join us for the day. And
Sure.
yeah, yes, sir. So I think it's about time, 11. So I'd like to welcome you all for day 5 of week 2 of our summer school on deep learning hosted by IIITDMJ Jabalpur. We hope you have been enjoying the session so far. Today, we are privileged to have with us Dr. Jignesh S. Bhatt as a distinguished researcher and academician in the field of signal processing, computer vision, and deep learning. He currently serves as an assistant professor at IIIT Vadodara and brings over 18 years of teaching experience and research experience to the field. He has contributed significantly to many gaining insights and understanding all the concepts. Thank you for joining us, taking time from your busy schedule and being with us. Thank you.
Thank you, Ishita. So, shall I share the screen?
Sure, sir, you can.
Okay, so is the screen visible to all?
Yes, sir, it is visible.
Can you see the slides?
Yes, sir, we can see the first page of the slide.
Okay.
Yes.
Should I start or are we waiting for someone?
No, sir, we can continue.
Okay, great. So, good morning, all of you. I'm Jignesh and I work as a faculty at IIIT Vadodara, which is located in Gujarat. So, first of all, thank you very much to IIITDM and Dr. Rakesh for the nice invitation and considering me as to contribute something in this first summer school on the deep learning. It's very encouraging steps. So, I congratulate IIITDM for this initiative. Can I know roughly the target audience background? Are they all faculty members or PhD students?
Well, so we have like a variety of people. Many of them are children, students, PhD scholars, or even faculties or people who want to exceed in this field. So we have got a pretty varied set of people here.
That's okay. I just wanted to confirm so that I can land in the topic accordingly. That's why. Okay, so the topic which is we are going to discuss today in the next 2 hours is unsupervised learning and generative modeling. So we'll go like this. We'll first see the introduction and then we'll move to autoencoders. for understanding how a neural network learns unsupervisedly. And then we will build our intuitions on generative processes. And from there, we'll take up to variational autoencoder, which is one of the generative models. And then at the end, we will see some of the applications and a few works which we have done at our laboratory for autoencoders and variational autoencoders and other generative models. So this is how we have planned these 2 hours. I hope my voice is clear enough and the slides are changing.
Yes, sir, your voice is clear and we can see the slides when they're changing.
Great. So we'll start with the meaning of unsupervised learning. So I think needless to say, we all are aware what is supervised learning, what is unsupervised learning. But even though to keep a pace of the presentation, we have kept one slide to explain you what is unsupervised learning. So basically, it's a class of learning algorithms that analyze and cluster the unlabeled data points. So the meaning of unlabeled data points is typically many times we have a large data, but we do not have the clear-cut labels associated to each one of them. So in such a cases, if we want to use neural network or learning algorithm, then we need to discover a certain common patterns which are there in the certain data set. And then we can group them together depending upon those common properties which are found. So as an example, you can see that in this particular slide, we have shown some objects on the left, which we labeled as raw unlabeled data. And then when we apply any unsupervised learning algorithm, typically it finds out the common properties among the data points. And you can see in the output, they all are clustered. So we say that the common properties among these different animals, the pictures of these animals are grouped together, and we found that these are the different types of the objects present there. So this is a very broad meaning or the sense of the unsupervised learning. When we look at generative models, so you can see the term generative models means it tries to generate something given some input, right? So if you look at this diagram, you can see that the input of this generative models are a certain data points. Now, these data points could be a few uh, speakers, vectors, or maybe a few images or few videos, right? So it could be any kind of the data points. And what we are expecting from this generative model is to generate similar data points in the output. So for example, just to illustrate the concept, in this diagram, it is shown that there are few pink balls and few green balls. So when we take these points into the generative models, it learns the underlying distribution of these pink balls and the underlying distribution of the green balls. Now, once we learn the underlying distribution, we can actually draw different numbers from those distribution. That means we can actually generate few more data points from the same distribution. So you can see in the outcome, there is a certain category of the distribution is shown where you can see few pink balls and few dark pink balls or few lighter pink balls. So this is to indicate that it is the model is trying to learn the underlying statistical properties of the data points and try to generate few similar data points, not the same. Similarly, you can see for the distribution associated to the green data points, where you can found different colors of the green ball. So this is to indicate that the idea of the generative model is to learn the underlying statistical distribution of the data set and provide us with a new similar data points. A very famous example, a classic, what I can say, a website is there. I'm sure many of you might have explored it. So if you're not explored, you can just click on this presentation. I will share these slides to your organizer. They will share it to you. So if you look at, if you click on this, you will come to know a live learning model, a live generative model, which can actually generate the fake face images of the humans, right? So this is just an example which shows that what a generative model do in general. So the topic of the presentation is unsupervised learning and generative model. So we will learn two tools now. In the first one, we will learn autoencoders, where we will get the idea of the so-called unsupervised learning, or how to encode the input data set in a very efficient manner. Okay. And in the second half, we will see how the variational autoencoder can convert a normal autoencoder into a generative process. Okay, so this is the plot. This is how we will take up this presentation. So let's start with the autoencoder. So as you can see in this diagram, the autoencoder is a typical artificial neural network which learns the efficient representation of the unlabeled data. Now, this sentence looks like very abstract sentence, right? And it's not a sentence to grasp what it is actually doing. So to make you understand, let us look at the definition. Okay, so as you can see on the slide number 6, I have written a definition of the autoencoder. So if you read this, it is a neural network with typically single hidden layer. There may be more, but to start with, we'll take a single hidden layer that is trained to attempt to copy its input to its output. So it's an attempt to copy its input to output. Now go back to our illustration of the autoencoder. So if you can see that in the input, there is an image of number 5 is given, which will be converted into a vector form as the X. Then this X will be encoded in a certain way. Now, the meaning of encoding is we all have learned different types of the coding where we convert a certain set of numbers into a certain different set of numbers, right? And the purpose of doing typically such conversion is first is to represent the same information in a different way for a different source. Okay. Then number 2 is, since your information may be very large, you would like to make a compact representation of it and you can share with the other users, right? So these are the purposes for which I think we have learned various encoding techniques in digital systems. You can imagine, to start with, that you have a certain encoding system, right? So let's say if I take a digit 5, and if I ask to convert it into binary, then there is a rule, right? And that rule will convert this 5 decimal into a certain code in binary. So I'll call it an encoded output. So that I will be available at bottleneck layer, right? Which is written as the latent representation of the input. Now I'll explain you what is this term. But for us, it is, in this case, in the example, we are converting it into certain binary numbers. So there is a rule. There is a deterministic rule. to convert a decimal number into a binary number, right? And with the complementary rule, we can convert this binary number back into the decimal number by decoding it. This all we have done, right? But if we do this, we may get the same input reflected in the output. That's not the purpose of the autoencoder. So if you read the definition, it is mentioned that it is attempting to copy. It is not copying. Now, if it is attempting, that means it is taking a certain properties and copying it, and it is dropping a few properties in the output. So to indicate this phenomena in the image, in the figure which is shown as an illustration, you can see that the way in which 5 is written in the input and the way in which 5 is written in the output is slightly different. This is just to tell you that the logic of encoder and the decoder in our case, in the neural network case, will not be fixed. That means there is not a standard equation which will take this input and convert into a certain coded form, and then the complementary equation will get it back. Okay. Rather, we will try to write down a loss function. We will try to write down a loss function between x and x tilde or x hat in such a way so that x hat will be almost like x. Mark my word, x hat in the output will be almost like x. That means it will not be x. There will be certain properties from the x will be dropped, and so that nevertheless x and x tilde or x hat would be almost similar, but few properties will be dropped. This is like a projection. All of you must have learned projection or filtering in a certain part of the mathematics, right? Wherein we take a projection of a vector onto certain plane or things like that, right? Where a few properties of the input will be dropped. So this is actually the central idea. So the practical term which is associated to the kind of the autoencoding process is the projection. And this projection or this filtering, we would like to do not by a deterministic rule, but by writing a learning algorithm where your machine will be exposed to certain input sets and expected to generate a certain other form of the input. And in the process, while the machine is trying to copy this certain input to output, it will learn certain properties. And that property are the weights associated to this bottleneck layer, right? And that's the latent representation of the input. So we say that this is a compact kind of a code or a succinct information which is stored for your input data set. So in the application, we can actually neglect this encoding process. We can use this latent representation in the inference and we can decode the output. This is the application of any autoencoding system. So to make your concept more clear, there is a block schematic shown in the next slide, in the slide number 5, where the input X is mapped to code H, which we call hidden layer, right? And there is a function F, which we are calling encoder. So it's like writing a function on the X. So F of X will be H, right? And from the H, if I use exactly complementary function from the F, I'll call it decoder, which is G. So if I apply G on H, I should get X back. Now here is a point what I was trying to stress you. If it is a deterministic rule, fixed rule, then from decimal to binary and from binary to decimal, the information can be exactly recovered. But here, our purpose is not to do that. Our purpose is to make an attempt to copy. So I will say that this X has a certain set of the properties. I will not copy all the properties from X to R. Okay. If I copy all the properties from X to R, this code is like a simple wire, electrical wire, but it's not that, right? It has a certain projection property. So selected properties of the X will be copied, represented in a compact form where it is written as H, decoded, and get the R back. So your R, which is the reconstruction, will be slightly different than the X. It won't be completely different than the X. Okay. We expect the distance from X in the R should be less, but should not be 0. Okay. So this is the actually the fundamental idea behind the autoencoder. So in the deterministic way, you can, as I have written on the slide, the function h can be written as f of x, which is your encoder, and the function r you can written as g of h, which is decoder. If you want to understand the same thing statistically or in a stochastic sense, you can say there is an underlying probability distribution, conditional probability distribution of h given x for encoder, and there is an underlying probability distribution, again conditional probability distribution of r given h as a part of the decoder. So you can actually interpret your autoencoder in both the sense, in the deterministic sense from the algebraic form, and also from the statistical sense, where you can say that it is trying to learn certain probabilistic properties. Okay, so this is what in the next slide, whatever I have written is what we have explained actually already, right? So you can go through this. This is exactly what we have explained in the previous slide. So I've written like a definition, what are the function of the encoder, decoder, and what is the objective. So our objective is to minimize the reconstruction error between the input and output. That means while we are copying or attempting copy, will leave certain properties. That's the point. Now, with this concept, we can actually have varieties of the autoencoders which are possible. We can construct undercomplete autoencoder or overcomplete autoencoder, and we can have a different regularized versions of the autoencoder like sparse, denoising, contractive, stochastic. Okay, so we'll in the next few slides we will go through each one of them, and I'll show you the basic construct of each one of them so that you can appreciate the concept of the constructing an autoencoder in a different ways. That's the idea. Okay, so I'll give you the basic slide and the basic constructs and the application so that you can appreciate the working of the autoencoders. And the standard applications of the there are so many applications, but obviously the dimensionality reduction or any information retrieval task falls under the idea of the autoencoding. Okay. So moving on, yeah, Ishita, are you there? Yeah, Ishita, are you there?
Yes, sir, I am.
Okay, so I guess things are under control. You're able to see the screen change and voice and everything is okay.
Yes, sir, I am. There might be a slight problem with the bandwidth from my side because I might be leaving sometimes. But other than everything is moving smoothly. If there's
Okay,
something, I'll ask you.
okay,
Yes, sir.
okay, okay. So let's look at the idea of the undercomplete autoencoder. So the constraint in the undercomplete autoencoder is the dimension of the code should be much less than the dimension of the input. And I guess this is very standard constraint in most of the coding scheme, right? Where So if you look at this diagram, you can see that something is, we have written latent code. So that's your H, and the input data. So that is your X. So we are saying that we would like to force the autoencoder to capture only the most important features of the input training data set. And if we force them, how can we force them to do this? So for that, we need to penalize the the function. So we have two functions, right? One is f, which is there on the x, the input, and we'll call it encoding. And there is another function which is g, which will be applied on the latent code. So if you look at how to force the autoencoder only to capture the most important phenomena, lies in the idea of how do you define learning process. That is the loss function. Okay. So as you can see in this equation, the loss function is defined between the x and g of f of x. So it is clear that this x is your input and g of f of x. So if you look at f of x, so f is here at the encoder. So you are applying f of x, so you get h. And then on the h, you are applying decoder, which is g. So basically, this g of f of x is the output, which we have denoted as small r. So it's a loss function which we have written between the x and the r. Now this loss function can be different. It could be norm 2 loss, okay, L2 norm loss, or maybe L1 loss, or maybe L1.5 loss, or maybe L infinity loss. So different type of the loss functions you can define. And you should appreciate that when you change the type of the loss function between x and the r, you are asking the autoencoder to capture different types of the features from the input. For example, if you write down here L2 loss. So L2 loss, how do you write down? You will be writing norm of x minus g of f of x, norm 2. If you write down this loss function and give your input output and ask the autoencoder to train using the backprop, what will happen? It will lend into such a latent code which will try to minimize the Euclidean distance between the input and the output, right? So there is one set of values associated to that, that is h. Let us call it h1. Now, next experiment, you will write down the loss function as norm 1. So with the same x minus g of f of x, norm 1, if you write down, your autoencoder functions g and f will be forced to capture a different set of the parameters from the input. That means now your latent code will be h2, which is different than the h1, right? So this is what I was trying to emphasize here in the definition of the autoencoder, that they are actually trained to attempt to copy its input to output. So if you're asking to attempt to copy as a loss L1 norm or L2 norm or L infinity norm or L1.5 norm, every time you are asking actually a different properties of the input to be copied in the output. And in this way, you are learning different latent representation or hidden representation of the input data set. I hope,
Excuse me, sir. So
yes.
students have some queries. You can check it in the chat box if you can.
Oh yeah, sure.
Yes, sir. Thank you.
You can speak up actually, no problem.
Okay, so I'll allow them. Actually, we haven't allowed them to be unmuting their mics. I can
Oh, sure.
change the
Please.
permissions.
Yeah, please go ahead. Please go ahead.
Participants can unmute themselves to ask the queries.
Sir, where is H1?
Sorry.
Sir, the H1 and H2 you were talking about.
Yeah, so Juhi, I'm trying to explain you by imposing different learning processes in the form of L1 loss or L2 loss or L1.5 loss, you will be able to learn different latent representation. I have not written here H1, H2, H3, but I'm saying that for a same experiment, you can learn different representation in the form of H1, H2, H3.
Okay.
Yeah. Yeah, any other participant? Any query till now? Good to.
Sir,
Yeah, please.
sir, the constraints dimension of H is very less than dimension of X.
Mhm.
Like, can you justify more about it?
So basically, when we design the autoencoder, we'll put the, so these are all layers, I guess. You've done basics of the neural network, right? So
Yes,
these
sir.
are all layers. So if I put a smaller number of the neurons in the dimension of the latent code, right? Your autoencoder will be forced to learn the input property in certain reduced set of the dimension. This is what I'm saying by forcing. So we are in the design of the architecture, we'll force them to restrict to, let's say, only 7 neurons. Then whatever the input data size is there, after subsequent processing in the encoding, it will be forced to compactly represent the information in the 7 neurons values only. Am I making sense?
Yes, sir.
Okay. Yeah, any other participant?
Good morning, sir.
Morning.
Sir, is it like performing some kind of a compression using transform? Because
Yeah. It is a kind of a compression. See, wherever you do under complete autoencoder, it's a compression. I believe the classic example to understand this is principal component analysis. I believe all of you have done it.
Yes.
Who has asked the question? I cannot read the name.
yes, sir. Yes, sir. Principal dimensionality reduction we use.
Exactly. So you can see in the principal component analysis, you write down deterministic function. What you do in the PCA, you take the data, you calculate the covariance matrix, and then you find out the eigenvalues and eigenvectors. You arrange the eigenvectors in the order form, you get a matrix. That's an orthogonal matrix. So it's a fixed matrix for your input, right? And it's a linear orthogonal process by which you are actually projecting your input on the variances, right? So you write down the equation for it. But in this under complete autoencoder, you will not write down any equation for encoding and decoding. What you'll do is you take the x. Yeah, someone is speaking. Rishiraj Vyas. Yeah, any issue?
He might have accidentally unmuted the mic, sir. No issue.
Okay. Yeah, so you get it, na? So basically, here we are not writing the explicit expression, but we are writing a loss function in such a way so that ultimately it will go to, if you write down the L2 loss, it will go to, in a statistical sense, to maximum likelihood estimation, which is your PCA. So if I take a linear decoder and invoke the L2 loss function here, the undercomplete autoencoder will turn into a principal component analysis. Now, if I tweak my loss function from L2 to L1.5 or maybe L1, then that PCA in the context of the PCA, because you've done it. So in the context of the PCA, that orthogonal matrix, we are skewing it up. So we got a feeling like a kernel PCA where we are changing the kernel non-linearly. Okay, so the processes and machineries are same, but here we are doing the same process through learning from the data. That's the idea. So a typical application is speaker recognition, where you can recognize the speaker from a certain invariant small set of the values. You do not require the complete voice signal to identify it, right? So that's one of the applications of under complete autoencoder. Similarly, you can have over complete autoencoder. So as you can see, if you choose to expand your basis into a certain higher dimension than the input, then you have a something called as an over complete autoencoder. So you will force your hidden representation to expand in the terms of the basis. So if you know a very classic example in the signal processing of basis expansion is a wavelet transform. So when you do wavelet transform, you are actually capturing the spatial or temporal as well as the frequency domain representation. So you are trying to achieve certain kind of the localization in a dynamic sense to increase the multi-resolution phenomena. So for that, what you need to do is you need to expand your basis. You are not supposed to decrease your basis function, right? So for any kind of the subspace clustering application where you can use wavelet kind of the features, you can realize such phenomena using the over complete autoencoder. When, as it is written, the latent space dimension will be much higher than the input. Again, you can have this loss function. So I have not repeated that thing, but again, you can write down the loss function in a different ways to realize different types of the over complete autoencoders. Now, apart from this under complete and over complete, the basic idea behind the all autoencoder is to perform regularized autoencoder. Okay, and this is directly from the basic concept of the regularization, wherein you have two terms in the loss function. First is your data reconstruction loss, and the second one is your penalty function associated to the particular regular. Yes, someone is speaking. Any issue? Some participation?
No, sir. Please continue.
Okay. So, as you can see on the slides of regularized autoencoder, the idea is to use a loss function to have certain other properties besides being ability to copy input to output. Okay. So if I choose a particular kind of the penalty associated to the input, let's say if I choose sparsity of the representation, I'll be having sparse autoencoder. If I choose the derivative of my representation should be smaller, as small as possible, then I have something called as a contractive autoencoder. If I choose to have a robustness to any noise or any missing input, I'll be having something called as a denoising autoencoder. Remember that in all these regularized autoencoders, there will be basically two terms. The first term, as you can see on this slide, is a loss function between x and the g of f of x, which is same as your standard under complete or over complete autoencoder. But together, there is one more function which is going to be minimized. And in this slide, I have written is as omega of h. So omega is a particular kind of the penalty you are putting on the h. So you are forcing that Now my solution will be, let's say, for example, L2 loss in this first half. But for an L2 loss, also we are adding certain more properties. For example, I'll add sparsity. So I will choose only those H out of the L2 which are sparse. So I believe you know what is sparse. The sparse means there will be a long vector, but a very few entries will be non-zero. So it gives you further compactness in the representation, and it has a very interesting statistical interpretation, which I have not discussed here because of the time limit, but it actually extracts very interesting statistical features of the data, and that is why the sparse autoencoders are very much useful when you have a big data and you can actually code them in a very compact form using applying the sparse penalty. Okay, so in all three, whether it is sparse or contractive or denoising, you should remember that the first term, the first loss function will be there, but the second loss function, omega on h, every time will be different. So if I invoke sparsity there, then there will be the entire loss function L plus omega will be minimized for a certain property of sparsity. If I do it contractive, then the entire loss function will be minimized for contractive loss. Likewise, okay, and these all have a certain application in the real world. That is why we are invoking different types of the penalty on the representation. So as you can see in the denoising autoencoder in the diagram, in the input we will give some noisy version. Let's say some number is there, 6 from MNIST dataset, and then in the reconstructed we'll make it clean. So how this two will be achieved? When you give a noisy version of the input here and you give a clean version of the input here, while this process of the denoising autoencoder will be performed, your autoencoder will learn certain properties of the noise. I repeat, it will learn a certain properties of the noise in the input data. If I give another digit here, which is slightly noisy, and ask to reconstruct, this network will, in this practice of minimizing the loss function, it will learn certain properties of the noise of the input. Yeah. If you keep repeating it, the encoder decoding process will be trained to learn a certain type of the noise. That means this denoising autoencoder may be useful to remove Gaussian noise, or maybe Rayleigh noise, or maybe some other kind of the noise which is there in a particular application. Okay, so for example, you are doing MRI denoising or CT denoising or remote sensing data denoising, right? So you know from your application domain that different types of the data is associated or affected by a certain type of the noise. So instead of modeling it in the hard code form, in the autoencoding process, we can give certain examples of the images which are affected by the Gaussian noise, and in the output we can keep a clean image. When we ask the denoising autoencoder to minimize the loss function, in a way it will learn the latent representation of the noise, and it will clean up your any unseen input in the future, right? So in the inference case, we do not require encoder. In the inference case, we just need the latent representation. You put your test image on the latent representation, it will decode it and it will give you the reconstructed output. How it can give you? Because while you are training this denoising autoencoder over a certain set of the images, it has learned the properties of those noises. And when you give a test input, it will reflect on that input, remove the noise, and it will give you the reconstructed output. So it's a game of how do you write down the loss function. Okay, loss function plus the penalty associated to it, and it will give you a form of the regularization on the learning the latent representation. Okay, so in the same way, you can have contractive autoencoder where you can choose certain basis of the latent representation where it will minimally change. Now, the real application of this is when your X will change slightly, when your input is changing slightly, in many applications, you do not expect the output to be changed. For example, your microphone. In the microphone, if I'm speaking and if there is yeah, hello?
Yes, sir. In the previous slide,
Okay.
sir, here the loss function will also have omega x,
You have to write down it. Yeah, you have to write down that.
and that will consist of the denoising part.
Correct. Exactly.
Okay, sir. And in the case of speaker recognition, the encoder will accept the input as a 1D vector, right?
Yes.
And in case of the denoising part, it will directly accept the 2D matrix, or we need to convert it into the 1D again.
Oh, see, these are all, so this is all depend upon how you design your network. This is architectural type of question. I can have a 2D convolution, 3D convolution, 1D convolution, right? So
Okay.
that is architecture.
So, sir, encoder can accept input in any form. It's not mandatory that it should be
Again,
black
how
and
do
white.
you again, Juhi, how do you design your architecture? It depends upon that.
Okay.
See, there is one thing that one is hardware, and another is how do you learn the software for it. तो आपने एक hardware बना दिया, so your hardware is, let's say, it is working on tensors, so it will take the tensors as the input. If your hardware is limited, it may take vectors as the input.
Okay. Okay, sir.
Okay, so similarly, you can see in this, yeah, so I was trying to say that suppose I'm speaking in the microphone and there are smaller noises around it, but I don't want the output to get affected and amplify those smaller changes also. So amplifier is designed in such a way so that the nearby smaller noise signal should not be get amplified and given the system. Otherwise, it will affect the fidelity of the system, right? So likewise, if you see, there are so many real world applications where we want that if my input changes slightly, my output should not change drastically. It should also change slightly also only. That means the latent code of the representation H should be the derivative of that should be very, very less. So I'm expecting a smooth H function there. And for that, I can impose something called as a contractive loss function, right? Where we penalize the encoder in a slightly different way than the sparse autoencoder. So the method I have shown here, and I will show you some of the application where you can actually see this. Towards the end of the logic of the...
What does the sparse constraint do?
Sorry?
What does the sparse constraint do?
So, Abdul, what do you mean by sparse vector? Do you appreciate what is sparse?
No, sir. I don't have idea of that.
Okay, so sparse vector is a representation of the data where your input and the output. In the output, you will be having only a few non-zero entries. That means, if you read the theory of compressed sensing, you will realize that there is a method by which we can actually reconstruct the data below the Nyquist sampling rate. You know what is Nyquist sampling?
No, sir.
Oh, so you are from which area, Abdul?
I'm in BTech actually, first year.
BTech first year. Okay. So in BTech first, you are in computer science or electronics?
Computer science.
Okay. So Abdul, in in the subsequent courses, you will learn how to digitize the data. So the process of digitization based on sampling the data, okay, at a certain interval of the time and coding them. So that means your continuous data set is not required to be sent. You can send a certain samples of it. And there is a theory which is given by Shannon Shannon and Nyquist, which is called the famous Nyquist theorem, which will say that if I want to code a particular sinusoid, I need to take the at least more than the double frequency rate of the sample. So if I have a 1 hertz signal, I need to take at least the 2 samples of it, minimum. I should take more than 2, but minimum 2. Then I can actually reconstruct the voice signal back in the digital form. This is the theorem which is celebrated by Shannon and Nyquist. So you will learn in your subsequent courses. But what I'm telling is, it is beyond Nyquist. In the 2006, you can search a paper by Donoho. Okay, and they have proposed a theory which is called compressed sensing. And the theory of compressed sensing say that if I have a data set which is written in the some vector form, I can actually have a coding technique which can actually compress this data below the rate of the Nyquist, and I can have a sparse representation of the data, wherein only a few non-zero elements will be there, rest all will be zero. That means I'm packing a lot of information in a only fewer bits. This is the property which is called sparsity. Okay, so when you invoke sparse autoencoder, you have an input. Let's say you have a voice of the speaker which is coded in 1000 what is that 1000 values, some real numbers, 1000 real number. So you have a vector of 1000 cross 1, but everywhere some non-zero values are written. If you pass it through the sparse autoencoder, you can have a compact representation of this, wherein only a few entries will be non-zero. So you are achieving highest possible level of compression, right? So this is what is the meaning of sparse autoencoders. Okay, so it has applications where you have a large data and you want to do certain multiple levels of the compression coding. Fine. I hope you are getting
Yes,
something.
yes, sir.
Yeah. Okay. So now moving on to what I can say.
Sir,
Yeah.
sir, won't there be any loss, major loss due to undersampling?
Yes, there will be, but there is a theory of compressed sensing which says that there is a guarantee, statistical guarantee of the information retrieval from the compact form. That means I can still retrieve statistically with a certain probability that information back. In a simple term, suppose there is a voice of Sai Abhinav, and I'll code it, the voice of the Sai Abhinav, with a certain coding technique. When I code it, naturally what Sai Abhinav was speaking earlier and now what Sai Abhinav is speaking now must be different. But I can still recognize that this is the voice of Sai Abhinav. That means recognition is still possible. There is a loss of information. So when the loss of information happens, it affects the fidelity of the signal. Okay, but it doesn't affect the intelligence of the signal. You can still decode it. I can say that, okay, this is the voice of Sai Abhinav, or even a machine can tell that from that compact representation that this is the voice of particular person. Is it okay? Are you getting?
Yes, sir.
Good. So we have a good listeners. So any issue till now? Then I can conclude this part of the portion by introducing you the deep autoencoder, and then we can move to something called as a generative processes. Till now, this is okay, right? So what we can
Yes,
do
sir.
is, what typically people do in the practice is not a single layer of the encoder and the decoder, but they will put certain more number of the layers in the encoding. So as you can see in this diagram, we have tried to show you there is one input layer and there are three encoding layer, right? So information is represented first in some gross form, then again some detailed form, then again some invariant form, and then again there is a bottleneck layer, right? And the decoding, of course, if you do three levels of the encoding, you have to do complementary three levels of the decoding. So now your F and the G are not the single layer, but they are multiple layers. So it is like applying a function on a function. I hope you are aware about the composition of the functions. I can sense there are many BTech students and they must be learning discrete mathematics and composition of the function FOG, GOF, etc. Right? So when you do composition of the function, you apply a function on a function. So you take X input, you apply a function, you get 1, you apply another function on it, apply another function on it. So you have a series of the function applied and you found a compact representation. This is what is deep autoencoders. Now, why do we do deep autoencoder? Why not only one? So basically, it will allow you to find out more and more invariant features of the data. You know what is the meaning of invariant features? Anyone?
Variance between the consecutive features is 0.
Which vary a lot among different images.
No. It is completely ulta. It is not like that. See, the meaning of invariant is the one which does not vary. Variant means if I say something is time varying, what does it mean? As the time moves, it changes. If I say something is time invariant, that means even though the time is changing, it doesn't change. This is the meaning of invariant, the one which does not change. So in most of the neural networks, our idea is to learn such a features of the input data set which are invariant. That means even if I change the input, there is a variation in the input. If I put face of one person, then face of second person, face of third person, face of the 500 person, you can see that the features are changing, but there are certain invariant features which will not change. What are those features? The features associated to eyes, the features associated to nose, lips, cheeks, eyebrow, your jawline. So these are the features which are broad features which will not change even if you take 500 images. Yes, there variations, a small variation may be there, but our idea is to classify whether it is a face or a car. So if I take 500 face images, I can learn a certain invariant features associated to face of the human. If I take 500 car images, I can learn certain invariant features of the car. Clear? Now I have two set of the invariant features. So if I give one image in the future to this network, the network knows these are the set of the invariant features of the face. अगर ये features आया तो ये face है, अगर ये वाले features आया तो वो car है. समझ में आ गया? So now if I give a car image, your model will match with what? With the set of the invariant features, right? So in the deep autoencoder, it will allow us to extract more and more invariant features of the data. That is why we are putting one encoding layer, next one more, right? So we are actually stacking up shallow autoencoders and we build a deep autoencoders. This is the idea of deep autoencoders. So we need to understand from the basic projection, filtering, autoencoding, regularized autoencoding, and then deep autoencoding. This is the flow. I hope this much is okay with all of you.
Sir, what will be the invariant feature in case of signals, like if it's undeterministic signal?
Undeterministic signal. What do you mean by undeterministic signal? Random signal?
Yes, sir.
Why do you want to analyze the random signal?
Not undeterministic, like we have the biomedical signals, so there are noises in that also.
Correct.
So in that case, what we'll consider as invariant features? Like for
See,
example, ECG or EMG signals.
So basically, in any data set, if you pick up any data point, there will be two content. One is data and one is noise. Where you will find pattern, in data or in noise?
Data.
Data. So where you will find invariant features?
In data.
In data. So the moment you invoke the deep autoencoders, automatically it will keep on projecting your certain features on the other features. But there are certain features you know that it won't change. Just for example, I'll give you a very clear example. I'll take a vector and I'll project it on a plane. I'll get a point on a plane.
Yes.
What if I project this point again on this plane? What will happen?
It will be a point only.
Correct. That means the process of projection is idempotent. It doesn't change.
Okay.
But in your process, in the encoding process, you're putting different filters. So you're trying to say, if I take this data point, project on this plane, is it changing? Then it will show a change. Now you say, if I take this point and project on a different plane, is it changing? You will see that there will be certain properties of the input data which won't change after a certain point. Even if I put 1,000 encoding layers in between, it won't change after the 10 layers. That will remain fixed. So these features will go into the bottleneck layer as the invariant features of the data. Did you get that?
Yes, sir. That means it's an automatic process happening
It's not
inside the
on.
encoder.
Wait. Nothing in this engineering world is automatic. It is how do you define the loss function. If you change the loss function, it will try to learn different features. It might change for that loss function. For example,
Okay.
between this input and output, if I once write down the L2 loss function, this encoder and decoder will be forced to learn something else. If I change the loss function between input output as L1, let's say, then this encoding decoding will learn something else. It is not automatic. automatic is the most dangerous term in engineering education. Okay, never say it is automatic. It is you, what you're writing the loss function. It is your intuitions about the understanding of the data that will make it to learn.
Okay, sir.
Yeah. So what's your background, Juhi?
Sir, my background is in electronics, but I have recently switched to the modeling of spiking neural networks.
Oh, great. So are you a faculty?
No, sir. PhD scholar.
Okay. Good, good. Spiking is a good area.
Yes,
Okay,
sir.
now
Thanks.
in the second part of this discussion, we would like to have something on the generative model, right? We need to learn something on the generative model. Okay, so let's build some intuition. So can you see the slide, Juhi? Is it visible?
Yes, sir.
So there is some picture. I'm asking you to rearrange. What is your response? If you rearrange this,
I'll try to
anything,
bring the same color part towards each other and then try to solve it
but
by joining the patterns.
yeah, I agree what you are saying. I'm asking what is this image? Can you guess the image?
It's a flower, sunflower, I guess.
It's a sunflower. Perfect. So it's a
Mm.
sunflower. Okay.
Yes.
Let's look at this one. Sai Abhinav, can you tell
Yes, sir. This is an image of a batsman hitting a ball in front of a wicket.
who is the batsman?
MS Dhoni.
Great. Look at the ability you have to observe the ability of human cognition. Even the data is scattered in this way, you are able to recognize is MS Dhoni. And the process what you are following is exactly what Jui has suggested. You are actually trying to connect these similar patterns together, make a picture out of it, and from your memory, you know this fellow is MS Dhoni, this is sunflower image. Okay, we have some other participation. Rearrange this. The first sentence, let's say, for example, who can rearrange the first sentence?
We have a holiday this Friday.
We have a holiday this Friday. Next one.
My
My
mom
mom,
cooks delicious
My mom.
cooks delicious.
My mom cooks delicious food. Next one.
Every
every
guest
guest
was
was
welcome.
welcome.
Likewise, I'm very sure that you can rearrange all these sentences which are jumbled. Now, the question here is this. Think about the process our brains perform while doing such operation. Just give 20 seconds and you think that what your brain is doing while you are rearranging a sentence or you are rearranging the pieces of the images in a jigsaw puzzle or a jumbled image.
ಕರೆಕ್ಟ್ ಆನ್ಸರ್ ಬೇಕು ಅಂದ್ರೆ ಇನ್ನೊಂದು ಅಟೆಂಪ್ಟ್ ಮಾಡ್ಬೇಕಂತ.
Sorry, I'm not able to understand your language. Some participant is saying something, but I'm unable to understand. Could you repeat it? Yeah.
So sometimes the mic gets unmuted by mistake, so I think we can continue here.
I see.
Sir, it's taking into consideration the words and the grammar of the language into perspective.
Correct. So basically, that grammars are the rules which we have defined, right? So given a sentence, we apply that rules and rearrange it. Same way in the image case of the image, we try to see the similar patterns, we get them together and make a picture in our brain, and then we say that okay, this is the out of this species actually it's a sunflower, out of this species it is actually MS Dhoni, out of this jumbled set of sentences, these are the actually the true sentences, right? Now if we can repeat this process of rearranging the data into certain order, certain pattern, then we can actually generate more patterns from the input. This is the intuitions behind all generative processes. You can relate this concept to random variables and a function of the random variable, right? So random variable is a function itself which take a sample point and then map it to real number, and then we assign probabilities to each one of them. When you write down function of the random variable, it's like a function on a function. So you have a real number and you will assign another real number to it. Okay, this is the technical idea behind generative modeling. Function of a random variable or a change of the random variable. So you might have learned a lot of discriminative models, which will given a certain data points, you will find out the classification boundary. So it's like learning the conditional probability between two classes, right? When you use generative models, you are actually trying to learn joint distribution of the input X and the Y. So basically you are trying to say, I can actually know from which distribution this data point is coming. And I also know from which distribution these data points are coming. If I know the distribution, I can draw more numbers from it. Did you get that? See, if I have a certain points, from this certain points, I know what is the sample distribution of it. If I have a distribution, I can choose more numbers from it. And each of this number will be belonging to the same distribution. That means I'm generating the data points given a data point. Did you get that? This is the idea behind generative models. So as an example, you can take in the Python, you can actually perform this experiment. You can take a 2D Gaussian data points and just plot them. So if you plot them, you can see that these are the random scattered data points. Now, if you apply a certain transformation, as I've written here, g of z, like this is like a function of a circle, right? Then if I apply this, then each of this point will be go and sit into a particular order. Because I have written this function like a function of a circle, this all scattered data points will change their position and be in a circular pattern. Now, if you look at the statistical distribution of this random data point, they are Gaussian. If you look at the statistical distribution of this circular data point, they are also Gaussian. That means we are not changing statistical distribution or statistical properties of the input. What we are changing? The relative positions by applying a function. It is similar to this exercise. This is like random data points belonging to a certain distribution. Your brain has arranged it and make it as an image. So you can say this is MS Dhoni or this is sunflower. In the same way, in the experiment, if I give you a certain random data points and give you a particular deterministic function, it may be a function of circle, it may be a function of square, triangle, whatever it is, then this data points will be rearranged in that particular order and you will have a pattern. जब आपको पैटर्न मिलता है आपको लगता है कि आपने डेटा को जनरेट किया. Did you get that?
Yes, sir.
Okay. So Juhi was saying that डेटा में ही पैटर्न होता है and which is very true. तो यहाँ पे जब आपको एक पैटर्न मिलेगा from random points, when you get a pattern, you will say I have generated data, but you not actually generated data. Did you get that? All generative models do not generate, they just rearranged. Okay. So to make it work, you need a machine to do it. And how do machine do it? The machine will operate on the numbers. So you need a set of numbers to be compared with another set of numbers, right? But here, the set of the numbers are in the form of probability distribution function. So as it is shown in this fundamental idea of generating data, you have a certain training samples from a distribution. You learn the underlying distribution. So you know, see, this distribution will not be given this input distribution. Only the training samples will be given to you. From these training samples, you will learn the underlying sampling distribution. Once you learn the distribution, you can actually draw newer samples from it. Okay? And to make sure that you are not generating something absurd, you make sure the input training samples distribution and the output distribution should be close. Agar input Gaussian hai with certain property, your output should also be Gaussian with certain property, as it was there in this example. In the previous example, the input is from normal 0, 1. Your output is also from normal 0, 1. You're not changing the statistical distribution, but you're just rearranging them. Once you rearrange, it is like drawing another samples from it. Okay. So then you need a measure. Then you need a measure that if I have two statistical distribution, how do I compare? If I have 2 points, I can compare the Euclidean distance or some other distance. But if I have one distribution and another distribution, how do I compare two distributions, whether they are close or apart? So we need a comparison measure, and that comparison measure, a very famous comparison measure, is divergence. And one of the most famous divergence is KL divergence. Okay, so interested may read about what is KL divergence. So KL divergence in a nutshell gives the measure of the cross entropy between the two distribution. So if they are far apart, their entropy will be high and then the KL divergence will be large. If they are nearby, the cross entropy will be less, and you can say this distribution and this distribution is closer. So we will be writing the optimization function now in the statistical sense, where we will be minimizing the statistical distance between P theta and PD. Okay, so this is the statistical optimization way. Okay, so you can see the taxonomy of the generative models in the literature. You will find there are fully visible, latent, and in the latent or hidden, there are two broad categories. One is the explicit likelihood estimation model, which are called the variational autoencoder, and you have a hidden models, implicit models, which are called GANs, generative adversarial network, right? Interestingly, both of this variational autoencoder and the GAN, they both are generative models. They both invented in the same year, 2014. They will appear in the two different conferences. Variational Autoencoder, I guess, in the ICLR 2014 and sorry, ICML 2014, and GAN is proposed in NIPS 2014. So ICML and NIPS are actually the two most tier 1 conferences in the machine learning worldwide. Okay, so in this particular topic, I mean, in this particular discussion, we will be not focusing on GAN because that is not allotted to me. I need to discuss something on variational autoencoder. So we will learn autoencoder, we'll make it variational so that the process of autoencoding will give us generative data points. Okay, so we'll have a generative models. So this is the idea. So the idea here in the variational autoencoder is to make the latent space stochastic. That's the single most idea. If you look at autoencoder, let me go back like this. If you look at this deep autoencoder block diagram, then you will see there is a bottleneck layer which is fixed. Once you train it, that values are fixed. What if I make this values stochastic? Stochastic means they're not fixed. They become random variables. So if they are random variable, it has a distribution associated with it. If there is a distribution, every time on my wish, I can draw different numbers from it. The time I change the set of the numbers, the time I'll get different output. This is what is variational autoencoder. Did you follow? Okay. So if your latent space is deterministic fixed numbers, it is autoencoder. If you can make it stochastic, if you can convert it into the random variables, then every time you have a liberty to choose different set of the numbers to represent in the form of the output, to decode them. And what you have in the result is variational autoencoder. So it will work like a generative model. And this is what is this diagram. Now you can appreciate this diagram. So in this diagram, we have shown that similar to the structure of the deep autoencoder, we have input, then we have a series of the encoders. But instead of learning the fixed number, we will learn parameter of the underlying distribution. What I mean by this? Parameter of the underlying distribution means, suppose I want to learn Gaussian random variables. That means I need a sample distribution which is Gaussian. So if I need to learn a Gaussian distribution, what are the parameters of the Gaussian distribution? Mu,
Mean and variance.
Mean and the variance. So in the Python, suppose if I give you a mean and the variance value, you can plot the Gaussian. If you give second time, it will give you a different type of the Gaussian with the same mu and sigma. That means you have the parameter, and through the parameter, you can actually generate different types of the Gaussian distributions from the same two numbers, mean and the variance. So now in the variational autoencoder, what we will do is, we will not learn the fixed set of the latent space values, but we will learn, for example, mean and the variance. So if I learn the mean and the variance of the latent space, I can actually, on my own, on my wish, I can generate a sampled version of the latent vector, which is denoted as Z in this diagram. तो ये जो Z है वो किस में से बनाया है? म्यू और सिग्मा. म्यू और सिग्मा कहां से आया? From the encoding process. So from the encoding process, we'll not learn a fixed vector 10 cross 1 or 100 cross 1, but I will learn two parameters, mu vector and variance covariance matrix or a variance values. Now using these two, I have a liberty. I can choose different ways and draw a Z vector from it. Every time if I choose different Z, in the output, X tilde will be every time different. This is in contrast to autoencoder, where there was nothing like a Z. It was a fixed number. Every time it will react in the same way when you give a new test input. Okay. But this one, this fellow, you have a chance. The designer has a chance or a liberty to choose how many values I want to draw from this distribution. And depending upon that, I have a liberty to choose and decode different types of the output mechanism. And this makes the autoencoder stochastic. And that's what is the term variational autoencoder. Okay, so if you read the sentence, it's a variational autoencoder is a generative model that learns to encode the input data into probabilistic latent space. That's the key. And decode the samples from that probabilistic space to reconstruct or generate new data. So for that, what it's required to be done, you need to see that it has to come from a specific distribution, right? So to choose that distribution, you can choose the P of Z. So in this equation, this P of Z is a liberty to the user. I can choose it to be Gaussian, I can choose it to be Rayleigh, I can choose it to be Poisson, okay? Depending upon what kind of data I am having. And with this PZ, I'm comparing Q of Z given X. What is Q of Z given X? If you look at this diagram, Q is the encoding function. Q of Z given X, X is the input. So you are learning a statistical distribution of Z given X, and you are comparing this statistical property with your assumed set of property. If your assumed is Gaussian, this will try to go close to Gaussian. If your assumed is Rayleigh, this will try to go close to Rayleigh. And this KL stands for KL divergence. So you are trying to minimize the KL divergence between conditional probability of the encoder and your assumed probability distribution function, P of Z.
Sir, this is similar to omega h that we were calculating earlier.
Sorry?
This is similar to omega h, the KL divergence part that we were calculating earlier, that omega h.
No, that's not KL divergence. Omega H is a fixed penalty. KL divergence is probabilistic penalty. There's a difference. This loss function will be minimized in a statistical sense. See, KL divergence will be calculated as the cross entropy. And cross entropy, how do you calculate the entropy?
Summation of minus P into log Q.
Correct. So basically, you will calculate the histograms. From histograms, you will be calculating the mutual information, then cross entropy, then you will be finding. So it's a statistical measure. Earlier, when I written omega h, it is a fixed property. It is not statistical property. You are saying the derivative should be small, the noise should be less. Here you are saying probability of Q of Z given X should go close to the probability distribution of, let's say, Gaussian or maybe Rayleigh, like that. So KL divergence minimizes the probabilistic distance between two distributions. One, Z given X, which you are learning from the data. The other one, P of Z, which you are assuming. You know from the problem that I am working on CT image and my noise should be Poisson. You know, you are working on MRI and my noise is Rayleigh. You know, I'm working on a remote sensing data and my noise is Gaussian. So you will learn those statistical properties of the data. You are forcing autoencoders to learn those properties along with the central loss function L of x comma x tilde. So please be careful in interpretation. So this is the same thing, but we have shown it as a building blocks where you can see that there's a training data and then there is an encoder. Then you will learn the parameters of the Z. Then you will, using this, you will choose one of the samples from here. And that sample will be passing through the weights of the decoder and then you will be having X. So this is the actually the building blocks of the variational autoencoder. This is a loss function. And you can see the first part is the constraint on the autoencoder, which we have discussed. And the second part is your log likelihood function, which is this. So you should understand this conditional expectation is the log likelihood function, which is this one, L of x comma x tilde. Okay, and this second one, this scale divergence is the regularizer on the encoder, which is in this is a second term. So it is ulta. I have written it this first plus second. Here in the VA loss function, I have written it other way. Now there is an issue in VA training which I would like to highlight, and then we'll see how it is solved as a trick, and then I will show you some applications. I think that would be end of our session. So let me see that it's a very good idea in the variational autoencoder that okay, you can learn the statistical parameter and then have a sample distribution and then draw different numbers from there. These are all nice, but let's put it in the practice. Suppose I want to train variational autoencoder. So I'll be using backpropagation for it. I will take the input, I will take the output and try to minimize the loss function by changing the gradients in the backprop. But you can see that all other steps in this variational autoencoder are differentiable except the one. And that process is sampling process. So since sampling process is non-differentiable, your backpropagation is not possible. Okay, so where is the sampling process? Once you learn these mu and big sigma, which is variance covariance matrix, using these two, you need to draw one sample of distribution. So sampling process is non-differentiable. So when you put this in the practice, your backprop will stop because you need to sample a distribution at that time if you want to go back to the encoder and come back to the decoder. So because this sampling process is non-differentiable, your backprop is not possible. So you cannot train it in a backpropagation sense. Okay, so now there are two ways. Either you train this VAE in some different way, not using backprop, okay, or you find out a way out so that you can run the backprop, which is very famous and available in the practice as an optimizer. Okay, so the author of this paper, they have found out a trick so that this step can be safely avoided away from the neural network and you can pass a backprop through it. And that trick is called reparameterization trick. So this is a trick. If you look at what is done, they have actually take this sampling process out and choose a number from a standard normal. So you can see N01, it is written. So there will be a epsilon value will be chosen from the standard normal and it will be get multiplied with the variance covariance value what your encoder has learned. and then added with the mu. So you'll get a number ultimately, and that number can be passed through this process. Now you can see that your backprop can easily pass through it, because now you have addition and multiplication instead of sampling. So the process of sampling, you're taken out from the neural network, and you are giving simply a number into it, and your variance covariance value learned by the encoder will be multiplied with that number. So multiplication is differentiable, addition is differentiable. So your all processes are now differentiable. That means you can still run the backprop, the famous Adam optimizer, to train your variational autoencoder process. This is what is famous as reparameterization trick in the literature. Okay, so the process of sampling from a standard idea of VAE is taken out, and it is implemented in a slightly different way. And if you want to know algebraically, then this is the slide. So the idea is change in random variables. So I believe all of you learn basic algebra and basic probability, where we do change of random variables, right? So when you do change of random variable, the representation basis will be changed. So in our case, Z is continuous random variable. So we have written Z is distributed as Q of phi Z given X. So Z tilde is expressed in the form of the parameter phi, right, in a statistical way. Now what we are doing? We are doing change of random variables. When you do change of random variable, your Z will be expressed in a deterministic random variable. So your Z tilde, you can look at in the equation 2, is now not statistically distributed, but it is equal to. But equal to what? G of phi epsilon comma x. So ये epsilon कहाँ से आया? Epsilon is coming from your standard normal, which you are choosing outside. So you have a library. For a standard normal, you have a library in the functions, in the neural network, in the PyTorch, everywhere you have a library, right? So you're not supposed to sample it. You already have it. You have to just draw a number and then add it. So your neural network will not be stopped while doing the backprop. So your statistical equation number 1 is now converted into deterministic equation, right? So you can see with this trick, the equation 1 will be working exactly as the equation 2. And with this reparameterization trick, your G of phi will be having a vector valued function. Okay, so with this trick, VAE training is possible using backpropagation. That means you can still invoke Adam optimizer while you are designing any variational autoencoder application. Okay, so this is the central idea behind the. If you want to know more, you can look at this paper of ICML 2014, and the author has given a complete proof for it. But what I bring over here is the main idea. Okay, so this is the idea basically. Is this okay to all of you?
Yes.
Yes, sir.
Great. So now let's look at towards the end of the presentation a few of the applications which are developed at our laboratory with our PhD students, our MTech student, BTech student, those who have worked with me on a various platform where we have used different types of the generating models for different applications. So one of the applications, as you can see on this slide, is super resolution, right? So in this work, what we have done is we took a medical data, which is very low resolution, ultra low dose CT images, right? So you can see these are very small X-ray grade images of very low resolution. Okay, and we raise it. So we first perform the restoration and then we raise the resolution of this by a factor of 2. So if you look at this third image, it is called SR-ULDCT. So it is super resolved. So the meaning of super resolution is if someone has a camera of 20 megapixel and some other your friend is having the camera with 40 megapixel. Now if you click a photograph from your camera and if your friend will click a photograph from his or her camera, naturally their his or her photograph will be better than yours. The reason is your camera is limited in the resolution. Okay, now what you are saying that though I have a 20 megapixel camera, I know a technique which is called super resolution, by which I will take my photograph of 20 megapixel and I will estimate another 20 megapixel from it. So my image will be as if captured from a 40 megapixel camera. You get that? So in the same way, that means if I have a 2 by 2 image, if I want to make it 4 by 4, how many new pixels I have to estimate?
12.
If I have 2 by 2 image, how many pixels are there? 4. If I have 4 by 4 image, there are 16. So I need to estimate 12 new pixels, which are not there at all in the data. That means it's a very tough problem. I need to estimate 12 new pixel values. And it is not like that I can estimate any random values. I have to estimate the values which are actually linked with what is that in the 2 by 2. So this method is called super resolution, where we insert newer values in between and make the images look larger without losing the fidelity. This technique is called super resolution. So GANs and variational autoencoders are used for such application to increase the resolution of the data. Okay, so in this case we have made an application, a product for medical, where even in the villages where there are no HRCT or something like that, even with the X-ray grade image, you can scale it up, restore it, and then make it super resolved, automatically colorized, and then you can estimate the what is that? How much percentage of the lung infection is there from the CT score, right? So this was very popular during the COVID time, and this work was actually been done during the COVID period, right? And then over the years, it has got matured. So this is one applications where data generating models are useful. In other application, yeah, please.
Is this guaranteed to reproduce the same image over and over again?
See, in a AI, all the guarantees are statistical guarantees.
So
Because
then it might be a problem, like for example, if it is super resoluting the low resolution image, then two super resoluting images might be different.
yes. All such things are there with the AI. That you should know, I guess. So all the test accuracies, all the generalization, everything is statistical. It is depend upon how large your data is, how large your network is trained, what is the stability, etc., etc., etc. So all the guarantees of any damn AI model in the world is statistical. Remember this. When someone say it is 98.9% accuracy, the meaning should be statistic sense. It should not be taken 98.9 in the absolute sense. It should be understood in the statistical sense. What I mean by statistical sense? The meaning is you need to see what kind of data set they have used, how much data set they have used, what is their size of the network, how many parameters they have learned, what are the constraints they have used, how many domain knowledge they have used. So many things you have to think. And then judge yourself that how much this 98.9 is valid in my case if I want to use it for my application. Did you get that?
Yes, sir.
This is not only true for this application, this is true for all application in AI across world. Right? That's why there is an area which is called explainable AI, which is emerging. Right? जो आप बोल रहे हैं ना, what is a guarantee? So people are there to look for it. What is a guarantee? What is a concrete guarantee that this will work like this? Right? Right now, all the AI models are working based on a specific data for which you are targeting the application. You take the input from the users or the domain expert. Okay. For example, in this case, we have shown this software to so many doctors and so many laboratory technicians and get it validated. Apart from our validation, this much accuracy, this much loss, etc., etc. All those are okay, nice. But then you need a expert validations for this. Those people, those who are going to use this software, right? So this is the best possible way to use AI. In another applications of data generating models, this is an application of image colorization. So you can see that still we have a lot of repository of grayscale images or grayscale videos which are captured well below ahead of the color cameras, right? And they're important. So we need to make a colored version of it by restoring it. So there is an application of autoencoder, convolutional autoencoder with the residual learning, which we have performed in this particular experiment. And then you can see that excellent results we have obtained for colorization. Even in this case of this, this jungle image, where you can see nicely the colors of this small petals of, and the leaves are green, and the sun shadow which is coming through the trees are still yellow, right? So these are the properties, these are the generalization capability of the AI model, which makes it so promising. Okay. By the way, Tanmay, who is the first author of this particular paper, is our BTech student. The first author of this particular paper of this idea of lung health visualization, Swati Rai, is my PhD student. She has graduated, so she's Dr. Swati Rai now. And there's one more work which we have done for cross-domain image translation, where you can take a certain type of the modality of the image and convert into some other form, and then convert back into the original form. So for example, you can see in this case, we have a CT image, which we converted into MRI and then converted back to CT. So we see in the generative model, we'll write down the loss function so that the loss between the input CT and the output CT should be minimum, right? So we can bound the generating process statistically. That's all from my side. I guess we are in time and we have certain 10 minutes for any question answer session.
Sir, can you please repeat that sampling part where parameterization technique you have explained?
Sure, sure.
So from encoder, please repeat that.
From where?
No, sir, the sampling part only. Please explain the entire process in this slide only.
This one, na?
Yes, sir.
Okay, so let's look at this slide. So you have a X, which are sample training images. So it is a trick to read this slide. Huh? Actually, these are all my handwritten notes. And Shalini, who is my PhD student, she took all the pain to convert this handwritten slides into machine form. So thanks to her, I do not have the patience to do all these things. Okay, so this is X sample training image. It will go into encoder. Your encoder will learn this mu and big sigma. So this big sigma is not summation, it is variance covariance matrix, right? And using these two, if I use this learn mu and sigma, I can sample one of the z's, right? And this z is drawn from what? It is drawn from normal of this mu and this sigma, which I have learned here in the encoder. So I'm inserting these two parameters into a Gaussian function and I draw one of the random vector from it. अगर मेरे पास एक Gaussian distribution है, Juhi, you are doing PhD, na? So this is
Yes,
the
sir.
question. This is the question for you. If you have a Gaussian distribution, if I draw a sample vector from it, let's say 1000 numbers from it, I'll find out the PDF of those 1000 numbers. What will be that PDF? What will be the statistical nature of that PDF? Did you follow my question?
Yes, sir.
हाँ, बोलो.
Gaussian.
Gaussian
Gaussian
आएगा.
ही होगा.
Correct? So
Yes,
Gaussian
sir.
ही आएगा. So
Yes.
this Gaussian vector, जो 1000 cross 1 का मिला, that I will take and I will give it to decoder. Yes? यही
Yes.
idea है ना? This is the idea. Every time, but the idea is every time I have a liberty to choose another 100,000 numbers.
Yes.
So if every time I'm choosing different 1000 numbers, I have something like a generative process. Every time this decoder will act differently and I have something different in the output. But how to realize this? Because if I have a distribution and if I draw 1000 numbers from it, it's a non-differentiable function. The act of sampling is non-differentiable. And in this case, at this stage of the slide, this sampling is performed within the autoencoder. So if the sampling is performed within the autoencoder, when I run the backprop यहाँ से run होगा ना, ऊपर से. Backprop will go from top to bottom here. So backprop will not be able to pass. Why? Because your sampling is non-differentiable. So your backprop training is not possible. Did you get what is the issue?
Yes, sir.
Now you look at the trick. What is the trick they have proposed? So the authors have proposed that you took this mu and put it as it is here. No change. Because mu is a number, you take it here. This sigma, which is variance covariance matrix, you scale it with a random number. You multiply it with a random number. But this random number, you will generating outside of the neural network, not within the neural network. So outside of the neural network, you have a dictionary of the Gaussian numbers. From that dictionary of the standard Gaussian number, you choose one number, which is epsilon, and you multiply this epsilon with this variance value. So you'll get another variance value.
Yes, sir.
But then when you add mu plus this sigma into epsilon, you'll get a one random vector. and that random vector will act as if you have sampled it from this. Did you get that?
Yes, sir, because the statistical properties will remain same.
Exactly. So you will get an effect as if you have sampled the vector, but you have not sampled it. You sample a number outside from it and you just insert in your neural network. So now if you run the backprop, you can see there is addition, multiplication are there. These are all differentiable. There is no sampling phenomena at all. So what you've done? You've done reparameterization. You've done a reparameterization of the Z, which was statistical in the first case. You make it deterministic by choosing a random number and multiplying with the your variance covariance value. That's the reparameterization trick.
Okay, sir. Sir, there is one more technique, like in spiking neural networks also we face the same problem because the output is in the form of spikes. So there's a technique of back propagation through time using surrogate gradients. But in
Correct.
that case, there's a problem that the gradients either get skipped or there's a vanishing gradient problem. So in case of training, for us for an artificial neural network for the same problem, if it's trained for like 500 epochs, say so. Technically, if we are using SNN, it should get trained within like 100 epochs. But what happens is when I like applied early stopping technique, uh, after 20 epochs, it was saying that now the training is not improving. So I was not confirmed like if either the gradients are getting skipped or it's a vanishing gradient problem. I was applying the BPTT technique using surrogate gradient, and the surrogate gradient was A tan H. But what I'm thinking is we can apply the same technique in that case also, or either it's like we have to compute the statistical parameters and only in that case we can apply this reparameterization technique.
Okay, I got your question, Jui. But what we can do is we can discuss separately. This is not a regular question on variational order. It's a slightly different question because you're working on spiking nets,
Yes,
right?
sir.
Yeah, so you can write to me, no problem. I have an email address. You can write to me if you want. We can have some different discussion also online, right? But I guess we have 2-3 minutes. If any participants would like to ask anything from the slides or any applications or any concept, let us take that first and then we can take it separately.
Okay, sir. I'll get back in touch with you on email.
Yeah, because your question is very specific to different type of network.
Sir,
Yes.
sir, the super resolution application can be applied to the satellite images, right? We can get a very
Yeah,
high resolution.
yeah. We have a lot of works. You can see my Google Scholar. You will find multiple papers on super resolution of hyperspectral and multispectral images. It's
Like
possible.
recently, I have come across an interview from ISRO, sir,
Yeah.
ISRO. So I came to know that the maximum or the highest resolution currently our Indian device ISRO satellite devices are able to achieve is around uh, 0 point some 75 something 75 meters.
Mm-hmm.
So with the super resolution, can we achieve the even more high resolution?
100%. So what you think? There are images on the Google Earth and all. Do you think are they captured at a so much high resolution? Do you think that?
No,
Then how they are processed? You tell me how you can see your road on the Google map so clean. Do you think that you have such a powerful camera lies on the 36,000 kilometer up on the Earth's surface and they are capturing this nice images? Do you think that?
no, sir.
They are all super resolved. They are all processed. See, as you must be knowing that as you go up, your resolution of the camera will go down.
Yes, sir.
So you need to process. So super resolution is a standard application in remote sensing or defense.
Okay, sir.
Yeah.
So good afternoon, sir. While using autoencoder for denoising, you have said that the encoder is able to capture the statistics or the characteristics of the noise, but how it is able to get a denoised version if we give a noise?
Not noise, data. See, any model we devise not to learn noise characteristics. Any model is devised to learn the characteristics of data. When it learns the characteristics of the data, it will not learn the characteristics of the noise. So if I have the points which are only reflecting data, that means in the output, I do not have the noise. So it is denoised.
Thank you, sir. Thank you.
Yeah. Yeah. Any other participants would like to have any questions? Okay, I guess we are on time.
Oh, yes,
So,
sir, we do.
Ishita, yeah, Ishita,
Yes,
so
sir.
over to you.
Okay. So, since all the participants' queries have been resolved, we can move on to the end of our session today. So, a special thanks to Dr. Jignesh Bhatt for not just explaining these complex concepts so clearly, but yet also making this session really interactive. And so, your practical examples were really helpful here. So, let's give a real big virtual applause for our respected speaker. And thank you again, sir, for joining us. And we'll be heading towards waiting for the next session with you for the practical session. Thank you.
Okay, thank you. And credits to participants, those who have asked the queries. If they have not asked the queries, I would have not answered it. So I am happy that at least they were listening. That is good. Thank you. Thank you, Ishita. So I'll be joining back on the same link, 2:30.
Yes, sir. Same link.
Okay. Thank you.
Thank you, sir.